This computer is the Intellect 8 Mod 80 made by Intel. This is the first computer to use an 8080 processor as its CPU. It came out in the middle of 1974, just shortly after the 8080 processor itself was introduced, and it was sold by Intel as a development system to companies that were going to embed an 8080 processor into products they were making. It's a fairly powerful looking little computer when you look inside. Over here on the left, we see an interface board to the front panel control electronics. And then this is a CPU board. We've got 3 RAM boards here, a total of 12K, 4K RAM boards each. We have some EEPROM boards here. This houses the monitor for it that allowed you to single step and set breakpoints and control other low-level functions for when you were doing in-circuit debug, for example. And over here on the right, we have a number of interface boards. One of these interface boards connected to this EEPROM socket you see on the front. It was an EEPROM programmer, which would have been important at this time because software for an embedded 8080 was probably going to be mostly on an EEPROM as opposed to loading from disk. It wasn't really envisioned that an 8080 processor was going to be a computer chip in a general purpose computer. It was more envisioned as being an embedded processor. Other interface cards here attach these ribbon cables that would then go into your target system to allow in-circuit emulation and in-circuit debug. And finally, one of the interface cards also connected to your teletype, which was your operator's console and your mass storage with a paper tape reader and punch. Now, the system could be used as an actual development system for software as well. So it came with an editor on paper tape, an assembler, so that you could develop here, or if you had access to mainframes or mini computers, they did have cross assemblers you could use as well. However, if you ever watched any of my other videos, you know that trying to write software using a teletype as your console and its paper tape reader and punch for mass storage is just miserable. It's extremely slow, it's noisy, it's error prone, and manipulating all those tapes is much more cumbersome than just having files on a disk, for example. And a company named Icom noticed this weak point and immediately began marketing a new floppy disk system, dual 8-inch drive system that you see here called the FD360. They began marketing this to the companies that had development systems like Intel. You look down here, you see they have hardware interfaces are available for the Intel Intellect 8 and some nationals. And it included that hardware interface is basically a board that plugged right into the bus that we were just looking at and hooked to this FD360. So basically, hardware is ready, just plug and play, just like that. In addition to those development systems, they already had it working on a couple of mini computers, an HP 2100 and Data General computers. But anyway, so as you notice here, there is no mention whatsoever of software. So even though the hardware is plug and play, it was up to you to then turn around and figure out, well, how do I make this disk drive integrate or be useful with the paper tape based assembler and editor I have? Now, this was really not that uncommon back in these days. It was not unusual for software to lag hardware by quite a while, if it even came out at all. So it wasn't as unusual as it sounds to have to do something yourself. And in fact, I did a 4-part video series on exactly this problem here, getting a version of the FD360 working with an early Altair computer that was running a paper tape based assembler and editor. How do you integrate that? If you want to watch that video series, I put a link to it in the description of this video. But anyway, you didn't have to wait long because a few months later, this was September of 74, in March of 1975, we see another ad from Icom, and now they're talking about not only do you have the hardware interface, but we have FDOS, floppy disk operating system available as well. And FDOS allowed you to do your software development with the floppy disk. It included an editor, a nice assembler. It was a macro assembler. It included commands and utilities to allow you to maintain all your files, maintain your disks, do backups. It included commands to import and export from external devices. For example, you could import from paper tape or punch to a paper tape. And you could do it in Intel hex format, which would have been a very standard interchange format, still is, frankly, as just like the paper tape would have been a standard format for interchange as far as media is concerned. So very nice system at this point. Basically 2 orders of magnitude faster when it comes to doing software development, loading the program, loading the editor, the assembler, and of course reading and writing files. Plus all your files are on the disk with file names. You can back them up much easier than using paper tape. Just a huge improvement. And as nice as this sounds, what really to me was remarkable was the time frame that this was available. Here we have a nice computer, that Intellect 8, running commercially available disk drives and a commercially available floppy disk operating system in March of 1975. This is much earlier than I expected because the Altair didn't begin shipping in quantity until about 1 month later, April of 1975. And it wasn't even close to this machine. At this point, the Altair was basically a box that had switches and lights, and that was all the I/O you had, and then 256 bytes of RAM. It would be almost 2 years until Altair and other S100 machines were equivalent to this system that we were just looking at in terms of having disk drives and a disk operating system. And we'll talk more about that in detail in just a minute. So as I did more research on this, it's tweaked my interest. From what I can find, FDOS is probably the first commercially distributed operating system to run on a microcomputer. And because of that, I felt it would be very important to take a look at it. It's a fairly significant piece of software that I ought to dig into. So that's what the rest of this video is going to be about today. Before we move on and look at FDOS and run some demos, let's go ahead and take a look at this timeline I just discussed by looking at this chart instead. Here in 1974, we move up to April or so, and we can see Intel introducing the 8080 processor. And a couple months later, the Intellect Mod 80 computer we've been looking at is available. And then a few months later in September is the Icom FD360 for the Intellect that we talked about being available. This is a dual 8-inch drive with a card plugged right into the Intellect 8, plug and play, but no software at this point. Now here's something we haven't talked about before, and this is a demonstration of CP/M 1.0 by Gary Kildall back in the fall of 1974 at some point. This was to let Intel see what he had developed. They weren't interested in buying it, and so they said he could do whatever he wanted to with it. He ran this demonstration on an Intellect 8 Mod 80 using custom hardware, custom controller and disk drive system put together by a colleague of his named John Torriday. I'm not sure I'm pronouncing that last name right, but neither of them turned this into a product or started selling it at this point. That would come along later. So by the time 1975 comes around in March, and Icom is now offering their disk operating system for sale, it becomes, from what I can tell, the first disk operating system commercially marketed and sold for a microcomputer. Here again, as we mentioned, in April or so, the Altair 88 started shipping in 1975. And at this point, the Altair was just a boring box with some lights, switches, and 256 bytes of RAM in it. And it would be quite a while until it was running disks in a disk operating system. And related to disk, we see nothing else of any importance in 1975. Now in 1976, here by April, we've got MIT's shipping the Altair 8-inch drive that they had just come up with. But it didn't run an operating system. It just ran disk basic. So you could load and save basic programs, you could load basic itself, and it worked with data files, but there was no ability to develop assembly language code or run native programs or run somebody else's programs. It was just basic. So this didn't really classify as a disk system with an operating system yet. Now on a side note sort of here, John Torriday, who made the controller for Gary Kildall to demonstrate CP/M on, did sell some of his disk drive systems and controllers along with licensed copies of CP/M during 1976. Now, it wasn't a lot of them. He didn't go out and advertise it as a product. It was sold mainly to friends and acquaintances. It appears that there might have been at least one of them sold back here in late 1975 as well. But it wasn't really pushed as a commercial product yet. That would come here in 1977, and we'll visit that in just a second. Another major thing in 1976 was the introduction of the 5¼ floppy drive from Shugart. And this would become the mainstay of the computer and floppy disk drive boom in 1977 for microcomputers. Now here in 1976, getting towards the fall, Icom announced an interface board and FDOS for the Altair, just like the one they had over here in the spring of '75 for the Intellect 8. At this point, Icom had already been purchased by a company called Pertec, who had also purchased Altair. So Altair and Icom are all actually part of Pertec at this point. So here we have an operating system and a 8-inch disk subsystem for Altair-style computers, including MSIs and others, in the late summer of 1976. So again, Icom might have been the first one commercially advertised and sold, even for the Altair class of computers. Near this time, too, MSI began advertising their dual 8-inch disk drive they were coming out with, but they were having real problems getting an operating system to work as they needed. So they ended up licensing CP/M from Gary Kildall at source level and modifying it and creating what they called IM-DOS. And IM-DOS and their first disk drives began shipping here in December of 1976. And that's also when the first North Star system started shipping. This is the breakthrough 5.25-inch system made by North Star that was just a fraction of the price of what 8-inch systems had been costing, and really caused the floppy disk market, and then in turn the microcomputer market, to just take off during 1977. Those North Star systems shipped with North Star DOS. So here at the end of '76, at the start of '77, we are now shipping disk systems with operating systems. Again, almost 2 years after the 1975 introduction of FDOS for the Intellect 8. This is also when we see the first ad for CP/M from Digital Research in a magazine, getting ready to sell it to the end customers. We also, in January, see a first ad from John Torday's company, Digital Systems, for his controller and drive. So he's starting to advertise and sell these now. And of course, 1977, the floppy floodgates just open. Everybody and his brothers making systems, mainly 5.25-inch. Every one of them has their own operating system. Interestingly here, August of '77 is when Altair DOS finally started shipping. So they announced it. They had a disk drive back here in '76, but it was a year and a half almost until they started shipping Altair DOS. All right, so during 1977, like I said, it's the Wild West of floppy disk drives. By the end of this, CP/M was getting more and more traction, and it was bubbling to the top as the one people tended to like. And then during 1978 is when CP/M really took off. CP/M 1.4 started selling to end customers, and then by 1979 and 80, CP/M 2 came out, and of course it then dominated the market for the next few years. All right, so that's some of the background on the comments I had made earlier and why I think this chart is saying that FDOS back in 1975 was probably the first commercially distributed operating system for a microcomputer. I'm not an official historian. I'm sure this causes some controversy, but this got to be one of the first, if not the first. All right, well, let's go ahead and move on and have some fun, and let's demonstrate and see what FDOS was like to use. I don't have an Intellect 8 computer, so instead I'm going to do this FDOS demonstration on this Altair 8800. Now, as far as FDOS is concerned and the disk drive and the interface board to the computer, it's virtually identical to what we would have seen back in early 1975 running on the Intellect 8. So this will be a very pertinent demonstration anyway. All right, so over here on the left, you can see the disk drive cabinet. This is technically an FD3712. This is the FD360 with the two Pertec drives placed side by side like you see here, instead of one above the other like it was in the original FD360. This allowed it to be put in a cabinet for a 19-inch rack, so that was the point of this drive. But other than that, it was identical to the original FD360. What you see here is the disk controller. This is identical to the one in the FD360. In the FD360 cabinet, this controller is up on its edge over on the right. Here, of course, it fits flat, where it's nice low profile for our rack cabinet, and it's wider cabinet, so it all fits. Now, what you're looking at is just half the controller. There's another board of equal complexity right below that one. You can kind of see the two-slot cage it's in. It's about 130 ICs altogether to implement the soft sector controller. Pretty complex back here in the days before we had single-chip disk controller ICs like the 1771. All right, by placing this controller inside the disk drive, that allowed it to stay the same no matter what computer it was used with. The only thing that had to change to work in a different computer was a fairly simple interface board like you see here. Here's the interface board that's designed for an S100 computer. So this is the S100 bus connection, and it has parts to interface to S100 signals, which would have been very similar in the Intellect 8 because it was also 8080. Now, as far as the disk drive is concerned, it connects right up here with a 50-pin ribbon cable. 3 parallel ports, 8-bit, are used to communicate with the disk drive. That's all it takes. And they're very simple ports. They're always on, always one direction. 2 of them run from the computer to the drive, 1 from the drive back to the computer. There's no hardware handshaking, so very simple to implement with just a small handful of TTL ICs. Now, the other thing they put on this board was some EEPROM and RAM. I have 1K of EEPROM and just 128 bytes of RAM. Now, in the board made for the Intellect 8, it probably would have been 1702s back in the day, 4 of them, of 256 bytes each, because this 2708 wasn't out yet at that point. And what's in that EEPROM is what's considered the resident portion of FDOS. It's low-level disk routines that never go away, so that when a program gets loaded into memory, it can overlay and erase FDOS, the transient part, and that really helped with memory because there wasn't a lot of RAM available back then. But the program that was just loaded could still do file I/O because the routines it needed were in the resident EEPROM. And in this RAM were a couple of essentially file control blocks, one for an input file, one for an output file, so that it could complete the I/O that it needed. And then when FDOS rebooted after a program ran, FDOS could come look inside this RAM and see the status of the files, close anything it needed, do any final updates. So that worked pretty well as far as FDOS is concerned. We'll see more of that later. So let's go ahead now and get this stuff put into the computer and get it all hooked up and run a demonstration. Let's go ahead and perform a complete cold start of FDOS from power off. Go ahead and turn on the computer and hit reset. To actually run the bootloader ROM, that's going to be the EEPROM we saw on the interface card. It's at C1000, so I've got this set to C1000. I'll examine that. And once we get these drives turned on, we can just hit run. It'll jump to that EEPROM and get us going. So turn on the drives. I'm going to run 2 disks and then just hit run. You can see the drive take off. You can see the activity on the front panel LEDs. It takes about 5 or 6 seconds. And there we get our startup banner from FDOS. Let's see if I get us a good view here. All right, so the exclamation point is the command prompt. And you can see here we're running FDOS 3 by the banner. So obviously this is not the first version of FDOS that would have been running back in 1978. Instead, this is a little bit newer. However, the difference between the versions is extremely small. And so if there ever is a difference between FDOS 3 and what you might have run back on the Intellect 8, I'll go ahead and I'll point that out. All right, now the first thing you might want to do is get a directory. So to do that, you type the list command, which is essentially a directory command. With no parameters, it lists the default drive, which is drive 0. If you want to look at the second drive, which is drive 1 in this system, you do a list comma 1. Now, any parameters you specify have to be separated by commas. It does not like a space as an alternative, and that took me a little bit of getting used to. All right, so now as you look at this, you can see that we got the file names on the left. The maximum file name length is only 5 characters. And I have to admit that is pretty restrictive to me as I use this. It's really the only thing I don't like about it. Otherwise, I'm pretty impressed with this. Even for operating systems from 1977 and on, this was not bad at all, especially since it was so early. But again, 5-character file names are still better than multiple paper tapes. It's still better than tape counters on a cassette player. So not great, but still better than what you had. All right, along with each file name, we can see where it begins on the disk in a track sector format and how long it is in a count of sectors. Each sector is 128 bytes. The file system on this was very basic, very primitive, not much to it at all. All files had to be contiguous on disk. They couldn't grow or shrink. And anytime you allocated space for a new file, it always came from the free space out past the end of all the other files on the disk. So as you would delete files, obviously if you deleted some of these, you'd end up with holes back in the disk area that aren't going to be used because it only allocates from free space at the end. So eventually you're going to have to run a command called pack, which moves all the files back towards the beginning of the disk and moves all the free space towards the end. Now this sounds pretty cumbersome. However, as small as the files you would typically generate back in these days, and as big as this disk was, you probably didn't have to do a pack very often. So it's not like it was in your way daily or on frequent use. Another good thing about contiguous files like this, though, is of course their performance is optimal compared to something like CP/M or MS-DOS with a fat table, where files were allocated with blocks, didn't have to be contiguous, much more convenient in the end, and that's of course the way operating systems went. But you had issues of fragmentation, and it might be slower depending on how spread across the disk the different blocks were. So that's one advantage of contiguous. Another big advantage in these early days is that the code is very simple, so it doesn't take much space, and we need to save as much RAM as possible back here. All right, so if you look at this, you can see we've got a few files you might recognize, like the assembler and the editor. Here's a linker and a librarian. Those weren't part of the original. The assembler just went straight to Intel hex. There was no option for relocating back in the original. So that's not so much System 3 or FDOS 3 as it is the fact that they're using a newer editor assembler here by FDOS 3. This file called exec, that is actually the command processor that we're running in right now. It's the transient or the loadable portion of FDOS. It always begins at track 1, sector 1. It has to be the first thing on the disk. That's the way the ROM, the boot ROM, knows where to find it. Now typically when you run exec and you start another program, most of these programs overlay exec, like the assembler, the editor, especially anything big, again, to take best advantage of RAM. And so it then has to reload it when it restarts. And we'll see how all that works in just a bit. All right, so in addition to some of these commands or programs like the assembler, editor, and a few other utilities, there's a number of intrinsic commands built right into the command processor. One we've already seen, of course, is the list command. That's our directory. There's a view command where you can look at a file. For example, I can look at a file called demo1. This comes to the console device, and it pauses for you so you can go through it page by page. You can actually back up if you want. I can hit P here, it goes back a page, or I can hit B, it goes all the way to the beginning. Or if you just hit return, then it stops. In addition to the console device, it supports a listing device, a punch, and a reader, sort of like CP/M would come to do as well. Right now, I have all these just coming to the screen. So for example, if I did a print of demo, it'll just come to the screen. That would have gone to a printer had you actually had it routed to a printer. Looks like there's a control character. To go to the punch is dump. And again, yes, I have it coming to the screen as well. You can see that goes in a little different format. It doesn't do tab expansion, it actually just included the tab. And then the reader is loaded with the load command. So you could send a file from a paper tape reader using the load command and get it into your file system here. So that allowed you to get some of the files in and out of this. All right, other commands that you would expect, for example, let's see, I can rename demo2 to demo5. And so now you've got demo5. And you can delete a file. Let's delete demo5. So now if you look, you see demo5 still there. It just changed the attribute to 99. That's what this column is. So 99 means it's deleted. So now if I went to try to view it, it knows it's deleted. It says it's not there. Anything you do says it's not there. But it's never going to allocate that space. And so frankly, it's basically keeping a backup for you. It's kind of handy. You can always undelete it using another command called change attribute. Whoops. Let's see. I think Control R repeats what I've got here. Change. I need another one. This is expecting possibly a teletype where it's echoing what you type. Okay, so change attribute of demo5 to 0. So now that undeleted it. You get your file back if you ever need to. I mean, you can kind of just keep your backup copies this way as well. So now if I did a view of demo5, you can see it. It can see it again. All right, let's see. What other types of commands are there? I'm drawing blanks off the top of my head. See, we've done deletes, renames, the pack command. I won't bother doing that. But anyway, so there's a number of intrinsic commands. But what will really show us how this works will be to do what it was designed for, and that is to edit and assemble programs that you were then going to run on your target machine, for example, if you were using an Intellect 8 for development, Or you might actually write some programs that run on this computer as well to enhance it. And I've done one or two of those, and I'll demonstrate those as well. So let's go ahead and just go through the assembler and editor real quick. Unfortunately, this video has gotten kind of long already, and to properly demonstrate the editor and assembler and how to use it, and also to see what it was like to code to run programs on this machine itself, and maybe a little bit of history as to how I got this all resurrected, it's going to just be too long for this video. So I'm going to split that into the next video. So be watching for that to come soon. Meanwhile, that will end this video where we get just a quick feel for what I believe is probably the first commercially distributed disk operating system for a microcomputer.